really appreciate it. I know carving some time out of the afternoon isn't an easy thing to do, so thanks again for joining us. We really appreciate it. By the way of introductions, my name is Dan Petito, and I'm an inside account manager with Design Point Solutions. I am joined by my partner in crime, Matt Devine, and Matt is a senior application engineer here with Design Point. He's basically going to be piloting the technical portion of today's webinar. Matt is pretty well versed in the SolidWorks suite of products, and he and I are excited to run through some of this with you all this afternoon. So thank you again for joining us. We really appreciate it. In the realm of questions, basically what we're going to do is if you could table them for the time being just to not disrupt the flow of the webinar, we'd appreciate it. We will pause at the end of the webinar to answer any questions that you may have. So table those for now, and we'll certainly carve out some time at the end to get those answered in the event that you have any. So in terms of the agenda, a couple things. So we are going to go through and demonstrate, or at least Matt is rather, demonstrate a static stress analysis study. Secondly, we will identify potential problem areas during injection molding process and seeing how design changes affect overall analysis. So we're excited to jump through some of this stuff with you guys. And once again, please table any questions that you have. We will be carving out some time at the end to get those answered. So yeah, let's get started. Matt, are you there?
I'm here, Dan. You can hear me?
I can. So Matt, I'm modeling this handle for a saw. Very interested in seeing if it's able to withstand all the forces that would be applied to it in a real-world environment. Obviously, I want to cut down the amount of prototypes that we make. So is there any way for us to do that within SolidWorks simulation?
Sure. So that's actually the purpose of our SolidWorks simulation tool, is to run through those static stress analysis on your assemblies or parts to see if they're going to go ahead and perform as you expected. So as you can see, you shared that model with me, so I have it open here on my SolidWorks window, and you can see it's going to be a handle for a saw. Now, with this handle, what we want to be able to do, and I would imagine, is it's going to be connected up to some other saw based off of this flat surface here and this flat surface here, as well as a couple bolt holes. So this bolt hole here and this bolt hole there is going to attach it to the actual saw body, and the rest of these are just going to constrain those two parts, the two halves of this handle together. So what I want to do, Dan, is just run through a quick simulation analysis to show you how to run through with the simulation tool and kind of the benefits that it gives for you. So I'm going to actually start off by going to my simulation pull down here and choosing a new study and call this handle test. Okay, so by choosing the static option, it's going to allow me to apply any kind of forces or pressures to this model. What opens up is a design tree similar to that in SolidWorks, if you use that today. And down here in the bottom corner, we're going to see a step-by-step walkthrough of all the different functions that need to be completed before we can run through and look at the stress results. The first area that we'll notice is the part and the material. So it actually brought over your material properties from SolidWorks. So that's a good idea that you had to actually model that material inside of SolidWorks, because now I don't have to look through my database to find it. So coming down through, the next step I want to add are the fixtures. So if I simply right-click on the fixtures folder, I can add any of those type of fixtures that I want to make. And as I mentioned earlier, I believe it's going to be fixed to the actual saw by these two bolt holes here, as well as the two down on the bottom. So all I'm doing is, without modeling the rest of this assembly, we're simply approximating the contacts that it's going to have with the rest of the assembly. Now, what's great here is I also know that I mentioned earlier, this surface and this surface are going to be touching the saw. So those two surfaces aren't going to be able to move a whole lot because they're actually going to be pressed up against the saw. So I'm just going to add this other roller slider fixture to approximate the rest of the saw being actually in this analysis. Now the next step as we walk down through the tree is the external loads. All we need to do is right-click here again, and you can see we can apply forces, torques, pressure, gravity, centrifugal or bearing loads. I'm going to start out with a force, Dan, because I know that you want to actually pull on this model. And then I'm going to simply select a few of these faces of the handle where your hand would actually grip it. So you can see all the visual confirmation on the screen right there. I can see how the pressure is actually squeezing in on the handle. And that's not really what we want in this case. We actually want to go based off of a certain direction. So if I utilize one of the reference planes that are in this 3D model, I can actually establish the direction of the force pretty easily here. I'm just going to type in 50 pounds. Dan, I think that's probably about how strong you are whenever you're pulling down on this handle. So we're going to estimate that at 50 pounds for my load. Okay, now once I have that set up, those are really all the steps that we need to actually run through one of these analysis studies. I'm just going to simply click the Run button, and SOLIDWORKS will automatically go in the background and create a mesh for us. That's basically breaking it down into a bunch of little tiny segments, and that's so that it can run through all the equations that it needs to actually solve the analysis for the stresses, displacements, and factors of safety. So once we get those couple steps run through, we can actually see some results here. And the first one that comes open is the stress results. What we're noticing here is the maximum stress in the model versus a displacement. And actually, I think that my values are a little bit high here, which actually leads me to believe that I'd made an error here. Instead of doing 50 pounds altogether, I did 50 pounds per item. So that enables me to easily identify if we make any mistakes when we're setting up the study. So I can reset that to a total force instead of per item. Using the per item force was actually making it 200 pounds total because it was doing 50 pounds on 4 different faces. So now as I take a look at the results here, we're going to see the stresses related to a 50-pound pulling force. You can see the maximum stress in the model is right around 900 psi. And if you don't know the strength characteristics of the material off the top of your head, that doesn't mean a whole lot. So I'm going to go ahead and move on to one of the other plots here, which is displacement. What I can actually see here is it looks like this part is actually displacing quite a bit. And in fact, I can animate these plots as well to get a really good understanding of how this is going to deflect. What you can see, Dan, from this model is it looks like it's deflecting a lot on the screen, but there's a deformation scale right here of 75 times. So it's actually showing it 75 times exaggerated than what it would be in real life. And in fact, it's only deflecting about 9 thousandths of an inch in real life. So that's a really, really small number. It's probably going to be too much for your eye to even see or notice as you're using this. So I'm going to say it's safe to say that that deflection is not unreasonable. Okay, but again, it just exaggerates it on the screen so you can understand that we put a downward force, and that's the way that it does deflect. What we're really interested in most of the time is a factor of safety. So the factor of safety is basically the relationship of the overall total braking strength of the part versus the strength that's on, or the force that's been applied. I'm going to say anything over 15 is too high of a factor of safety, and we're just going to simply use a call out here to show the minimum factor of safety. And what we're going to see is the weakest areas of the part is actually right around those connection points, which I kind of assume that anyway because we're going to have bolts running through there. So we can see those weak areas of the model. So there you go, Dan. It was pretty simple for us to go ahead and run through a stress analysis. We can see a 3.4 factor of safety basically means that you can apply 3.5 times more load than we did. So we can take that 50 times 3.4, and that's when this part will finally just start to fail. So it looks like overall a pretty safe design. I think you did a pretty good job with that.
Yeah, it was awesome. Just a good demonstration and a good walkthrough. Obviously looks awesome, but just FYI, as you may not know, I also designed this part with the intent of it being injection molded. So two things. How would I know if it'll fill properly? Plus, I also need to identify any potential problem areas we might run into during the molding process. And to be completely honest, I feel a bit stuck.
Okay. Yeah, I can see where you'd feel a little bit helpless there, trying to just know if this was okay or not to inject. So let me go ahead and use our SOLIDWORKS plastics tool since this is an injection molded part. I'm going to simply actually switch over to another configuration because how this part was built is it's actually 2 different halves that are bolted together. And we're going to inject 1 half at a time. So really that's all I need to do here is simply look at 1 half versus the other. So let me just get this model rebuilt here and we'll switch over to the half. Okay, so these are the 2 halves that are going to be put together, and I'm going to run through an injection mold analysis simulation on just 1 half here. So all we need to do is use the SOLIDWORKS plastics tool. So the SOLIDWORKS plastics tool is actually integrated right within the SOLIDWORKS interface, just like our simulation tool is. So we're not importing and exporting our data out to another system, which is going to save a ton of time and setup. You'll notice that the plastics wizard is very similar to the SolidWorks simulation wizard. A couple additional options there, but pretty much the same process. We basically just go through the mesh creation up top here, and once we go through those setups, we're going to simply come down through and choose the material that we want to work with. There's a very expansive database of materials built into the software. There's over 4,000 materials that come preloaded with SolidWorks plastics. And of course, if you have your own material data, you can always enter that information in there as well. So I'm going to simply use this Bayer material that I know is similar to the one that you're going to be using to actually inject this part. And then finally, we just need to set up an injection location or a gate location, as some may know it as. If you're having trouble looking at a part and just kind of identifying one of the best places to put your injection location, we can actually use the automatic wizard here to insert one injection location or one gate location for us. You can see whenever I do that, it includes the pointer over there on the model. I'm going to make it a little bit larger so we can see it easier. And that's actually the most optimum injection point based off of the flow length. So it knows that it's going to take the material a certain amount of time to reach this end as it is this end down here. And it tries to optimize that for you and put it in a great place. There's only one slight problem here, is that that's actually right on one of the functional faces of this model, and that's going to leave a nasty mark where that gate actually gets cut off. So what I'm going to do is actually move that very slightly. So I'm just going to delete the one that's there, and I'm just going to move that right up here to the edge of the part where it's going to be a little bit less noticeable. Okay, so once we do that, it's as easy as clicking OK and running through the analysis. Now, this one takes about 45 seconds to a minute to run through, so I went ahead and ran through the results ahead of time for you, just so you didn't have to wait for me to run those. But what you can see is the very nice results here, showing you exactly what we were looking for. So I think you mentioned fill time, or you may not have mentioned fill time, but that's one of the results that it gives you. And as we play through, we can actually see how this flow actually enters the model and how it moves around and actually fills the entire cavity. Based on that gate location, you can see that we have a pretty even fill. We might want to move the location down here just a little bit more because it does look like the top fills a little faster than the bottom. But that's okay for now. What I can eventually see in the end here is that the fill time is about 3.9, almost 4 seconds. So that's not that bad for just one part. But Dan, are you planning on building just one of these parts, or you think you're going to be building, thousands, tens of thousands, millions?
Upwards of 5,000 plus, so certainly more than one.
Right, so you can really see that if we can shave off some time in the injection mold analysis, it's going to save you a ton of time in the end. We can also look at features like pressure at the end of fill. So you can see our machine actually can handle 12,000 PSI. We're only at about 3,300 PSI here. So we know that we're only at about a quarter of the capacity of our machine. And that's actually a good sign here, so we can go ahead with the equipment that we currently have to go ahead and inject this part. There's a lot of other options in here that we can look at as far as results. The next two I want to focus on are the weld lines and the air traps. So the weld lines are basically giving you an analysis of where the flow fronts would come together and meet and cause not only visual defects, but they can also cause potential high stress locations and areas where it might crack. And then we can also take a look at air traps. So all those purple dots that show up are where gases may get trapped inside of this mold as it's injecting. Luckily for this design, we picked a pretty good gate location, and all those air trap locations are pretty much on the parting line, so they're going to be pretty easy to vent. So I'm not going to be actually too concerned about those air traps in this case. So overall, with this plastics analysis result, it looks like you did a pretty good job on the design, Dan. I think it's going to meet your strength requirements as well as eject pretty easily.
Yeah, it looks to be, and obviously still all in the SolidWorks environment that I'm familiar with already. So super helpful. Thanks for running through that. But I was thinking back, Matt, to that 3.4 factor of safety. Honestly, I think it might be a little too high for our purposes. I'm relatively convinced, we could maybe get away with shaving some material off of this part. We'd obviously be able to save some extra money if we were able to remove some materials. So how overall, would that affect the strength of the design if we were to potentially remove some materials?
So that's actually a pretty good question. Let's go ahead back and take a look at this model a little bit more in detail. What I can see right now is I have a relative thickness all around of 3 millimeters for the part, and the ribs are just about that same thickness. So because we're using SolidWorks, it's pretty easy to make model changes. And in fact, I already set up a configuration ahead of time with that smaller size. What we'll first take a look at here are the mass properties of this guy. So we're at about 3.85 cubic inches. Okay, so that's how much plastic material is actually needed to fill this part, 3.85. So if I activate another configuration, whenever I do that, you'll notice that within SolidWorks, that whole part actually shrunk down just a bit. Okay, so if we look at the mass properties now, our volume is right around 2.76. So really, we're at a savings of just over 1 cubic inch of material here just by shaving down the part a little bit. Now again, 1 cubic inch of material might not cost that much, but if you're planning on running, like you said, 5,000 plus of these, that can really, really add up significantly to a significant cost savings in the end. So even being able to shave down a little bit of material there is going to save a ton of money in the end. So now I know that your main concern here is really the strength, right? So as we shave down material, is it still going to perform as we expected? So I'm going to go ahead and switch back over to the full version of this model at the smaller thickness. And what's great here is that I can take that original handle test, and rather than set that entire simulation study up again, I'm just going to duplicate it. So once I duplicate it, I can call this handle test, and I'll just make it 2 for now, using my new smaller size. And it's going to automatically set up my study for me based off of the old study. So now, Dan, I saved a ton of time because I don't have to go back through and reset up all my forces, fixtures, and materials. All I need to do, click the Run button. It's going to go ahead and remesh the model, run through those calculations again, and spit out some new results for us. So a really great way to be able to test multiple versions of a design very quickly with the duplicate function. So now that I have the results, I can see the stress rose just slightly from about 900 to around 11 or 1200 psi. So that's not a significant jump. It's actually a little surprising. So I'm going to go and check the displacements. You know, we're really only displacing now about 13 thousandths maximum as opposed to 9 thousandths before. So again, that's still a very small number, and that might not be too noticeable if you're actually using this drill. So I think that we're, or this saw, I'm sorry, I think we're on the right track here. So if I take a look at that factor of safety plot again, you can see that it actually reduced your factor of safety here exactly from 3.4 to 2.7. We can see it's still in the same location. It's right around those holes where the bolt's going to go through, which is understandable. But we're really only down around 2.7. Now, Dan, from just looking at that, I would have said reducing the thickness that much is actually going to make this part fail, but it seems like you're actually still doing pretty well with this guy. You know, factor safety of 2 or less is probably what you want to avoid. So, you know, you're still up there in factor safety. So, it's pretty nice being able to do that stress test to confirm.
Absolutely, absolutely. And obviously, with that in mind, you know, since now the part has changed, I might be getting ahead of myself. Did you have something else you wanted to show here?
No, not for that particular case.
Okay, yeah, because now, obviously, with that in mind, with the changes in mind, we've removed some materials. We're saving some money in terms of materials. Obviously, now we want to be able to rerun that injection mold analysis now that we have a thinner part. I'm a little concerned it may not fill properly now. Is that right? Now that we, you know, the design has changed a bit since we last readjusted it.
Yeah, you know, that's actually a pretty good call. A lot of times when we have thinner walled parts, that can actually introduce some other issues such as race tracking, where a thicker section might inject a little bit faster and kind of cause an unwanted void in the model. So that's a good call that we should probably check that out now that we've made this a little bit smaller. So again, I'm just going to access another configuration that I had there inside of SolidWorks. So we're just looking at half of this. I'm going to open up the plastics analysis. And really, we can run down through this wizard again, just creating the mesh, adding the polymer and the injection location, and then finally taking a look at the results in the end here. And what we can wind up seeing is a pretty similar fill pattern. We can see it's going to fill from our gate location. It's going to wrap around. The top still fills just slightly faster than the bottom does, so I might need to, again, adjust that down just a little bit. But with a tool like this, that's something that you can always play with and test out. The one thing I really do notice here, though, Dan, that we didn't really anticipate is it actually changed the fill time. So because of the smaller cavities, the smaller thicknesses, it increased the amount of pressure of the fluid going through there, or the plastic flowing through the model. So it actually shot it in there a little bit faster. We're down to about 2.6 seconds instead of 4. Again, just like with the material cost, shaving off almost 1.5 seconds of this design is really, really going to improve your end result. you're going to be able to make 5,000 of these a lot faster if you take 5,000 times a second and a half. So just to verify some of these other functions here, we're going to look at the pressure at the end of fill. We're at about 6,000 PSI or 6,800 PSI. As I mentioned, the machine that you currently have, Dan, can run at 12,000 PSI, so we're still well within that working limit of your machine. So at least that's good. We know you don't have to buy a new machine and size up there. Again, looking at some of these temperatures, we can always do that as well. And then finally, I want to verify it with the air traps and the sink marks as well. And again, just like we saw before, because it's a very similar design, the air traps and the weld lines really aren't too bad. So those are mostly on the parting surfaces where we can easily get to with vents. The last thing that I want to take a look at here as well that simulation or the plastics can do for us is look at sink marks. So sink marks are actually visual defects or cosmetic defects that can be caused due to the hot plastic actually shrinking as it cools. And you can see we have some lines on the outside of this part indicating some shrink mark locations. And that's mainly due to the fact of the thickness of these ribs and maybe the radius that's on here of the fillets. So that's going to give me a nice thick region of material there. And as that cools, it's going to cool at a different rate than the thinner walled sections. So that's why we wind up with these sink marks here, which you can see identified by the software. What's great with that is it gives you the great visual indicator, Dan. So if you wanted to go back and do some more rework to this part, we could certainly try to thin out those ribs or change the radius there to minimize these sink marks even more.
Yeah, obviously we'll be able to save on rework's cost too. I mean, we're able to identify these issues before we go into production, right? So being able to kind of get a sense for where the issues are earlier on in the design process helps us avoid those future obstacles. So that's huge.
Exactly. So that's a great call there, Dan. You know, obviously, if you can save a little bit of time and money on one of these parts, go into a much larger run is going to save you a ton of money. And then again, if you have any kind of mold rework, that can be very, very expensive and take a long time actually to get your molds to and from the shop where that rework is going to happen. So all in all, these are really, really great tools for identifying some of these potential problems up front.
Absolutely. Yeah, and thank you for running through that. So, you know, I obviously see the value, you know, after running through and demonstrating some of the capabilities. So let's just take a quick snapshot of what some of our customers are saying. And, you know, just wanted to run through this really quickly. So, you know, we've gotten some feedback from our customers on them using SolidWorks simulation. And, you know, just to run through it really quick, you know, advantages of SolidWorks simulation, you don't have to transfer information back and forth between applications, right? So being able to leverage this functionality within the SolidWorks environment you're already familiar with is a huge advantage. So continuing on, SolidWorks simulation provides a much more cost-effective means for conducting analysis. Secondly, you know, with SolidWorks simulation, obviously I can identify and resolve potential issues during design. So then when we mold those initial pieces, they're right the first time. Continuing on, it's an incredible tool that's let us save 30 to 60% in capital costs in the development of new products, which is huge. So again, just kind of in closing and in summary, just to kind of go through some things that we went through. Obviously, we demonstrated the use of simulation to run a static stress analysis. Thanks so much for running through that, Matt. That was awesome. Obviously able to identify earlier in the design process how effectively an injection molded part will fill. Went through required injection pressure, determining gate locations, fill times, things like that. And we skinned down some of the parts on the design, as you guys saw, which we ran through. Easily rerun a study based off of design changes, as you can see. So again, you know, we really hope you guys found some value in the presentation today. We really appreciate you joining us. You will see a quick pop-up on your screen if we aren't having any technical difficulty here. It's just a quick question regarding some upcoming webinar topics that we're brainstorming. Obviously, your feedback is really important to us. We want to make sure that we're able to continue providing educational content as it relates to SolidWorks and your interest and your questions. So please give us some feedback on that. If it doesn't pop up on your screen for any weird reason, we'll be following up with an email with the quick poll. Again, very quickly, what are some upcoming webinars on SolidWorks and SolidWorks products that you'd be interested in learning more about? Again, we really hope to tailor future webinars around things that you're all interested in. So we really appreciate it, and your feedback is greatly appreciated. Also, any questions on anything you saw today or anything SolidWorks in general, feel free to reach out to me. Again, my name is Dan Petito. Here's my email address and my contact information. Let us know if you have questions. And again, thank you again, everyone, for joining us. We really appreciate it, and we look forward to seeing you next time. Have a great afternoon. And thank you, Matt.
Yep, thank you, Dan.
Have a great day, everyone. Thank you.